Suppose we have a 2 by 2 system of linear equations. Let's look at how we solve for x and y using the Gauss-Jordan method. Stick around and I'll show you how to produce an augmented matrix and then manipulate the matrix into reduced row echelon form. The system of equations we're asked to solve is shown on the board. The first step is to create a coefficient matrix by extracting the coefficients of variables x and y such that they become the entries in the matrix. This results in a 2 by 2 matrix. Next, we augment this matrix by adding the constant terms. We separate these from the coefficients using a vertical line. Now, we need to perform row operations such that the matrix is in reduced row echelon form. So what is reduced row echelon form? Well, we need to reduce our matrix such that it is in the following form. The row operations we perform produces a series of ones along the diagonal from the top left to the bottom right, and all other entries are 0. Now let's look at what rules we're constrained by when reducing the matrix to reduced row echelon form. Rule 1, we can interchange or swap any two rows. Rule 2, we can multiply a row by any non-zero constant. Rule 3, we can add or subtract any two rows, which can be done in conjunction with Rule 2, which enables us to multiply a row by a non-zero constant. Let's apply these rules to our system of equations and demonstrate a step-by-step technique to reduce our 2 by 2 matrix to reduced row echelon form. So for step 1, the first row needs to have a leading coefficient of 1. So we need a 1 in row 1, column 1. So we need to get a 1 in this position here. And we can do this by swapping row 1 with row 2. So this is row 1 and this is row 2. So if we swap row 1 and row 2, row 1 becomes 1, minus 1 and 1, and row 2 becomes 2, 1 and 5. And for step 2, we now need to use row operations to get zeros in all other entries of column 1. So there's only one other entry in column 1, and that's this entry here. So we need to make this entry a 0. And to do this, we can multiply row 1 by 2. So row 1 is this row here, and then subtract row 2 from it. So row 2 is here. And so this leaves the first row unchanged. So we have 1, minus 1 and 1. And then the second row becomes 0, minus 3 and minus 3. And for step 3, we need to use row operations to get a 1 in row 2, column 2. So this is the last entry on the diagonal of the matrix. So that's this entry here. And to achieve this, we can divide row 2 by minus 3. So row 2 is this row here. And if we divide row 2 by minus 3, we get 0, 1 and 1. And row 1 here remains unchanged. And for step number 4, we need to use row operations to make all other entries in column 2 to be 0. So we're only interested in one other entry in column 2, and that's this one here. And we need to make this a 0. And to achieve this, we can add row 1 and row 2. So this is row 1 and this is row 2. And if we add them both together, the new row 1 becomes 1, 0 and 2, and row 2 remains unchanged, so we have 0, 1 and 1. So now we have the matrix in reduced row echelon form. We can pick the values of x and y from the rows in the matrix. So from row 1, that's this row here, we get x is equal to 2. And from row 2, so that's this row here, we get y is equal to 1. And therefore x equals 2 and y equals 1 is the solution to our system of linear equations.